First of all, I am thankful to SANDHAN-AGIC, Sarvaiya sir, Jayanti Ravi ma'am, and Bhatt sir for giving me an opportunity to present my research work. I am Jigar Shah. I am Associated Professor in Chemistry in Sivasa Science College. Title of my research work is Supramolecular Synthesis, Characterization and Application. Now, what is supramolecular chemistry? Supramolecular chemistry is chemistry beyond the molecule, that is, chemistry of molecular assembles. Supramolecular chemistry focuses on the non-covalent bonding of the molecule having weaker and reversible interaction. These interactions are due to hydrogen bonding, hydrophobic forces, van der Waals forces, p-pi interaction, and electrostatic effects. Supramolecular provides molecular self-assembly, folding, molecular recognition, and host gas chemistry. Crown ether, cyclodextrins, and calixarine are class of supramolecular chemistry. Supramolecular chemistry can be classified into crown ether, cyclodextrin, and calixarine. Calixarine is a third generation of supramolecular host compound after crown ether and cyclodextrin. Calixarine is a large cyclic molecule made up of phenol units containing large cavity of molecular dimension, and due to this large cavity it has capability to absorb variety of other molecule, which is of great interest in the field of host gas chemistry, separation, purification, and slow and steady release of drug. By introduction of functional group into calixarine, make it possible for variety of other application like recovery of metal ion selective electrode, phase transfer agents, separation of neutral molecule, as catalyst, as HPLC stationary phase, metal ion extraction agents, and for construction of building blocks. Hence, we have synthesized para-nitrocalixyxerine hydroxamic acid for the separation and recovery of metal ion. This para-nitrocalixyxerine hydroxamic acid is synthesized by acid catalyzed condensation of para-nitrophenol and benzaldehyde, which is reduced by hydrazine hydrate in the presence of Raney nickel at 0 to 5 degree temperature to give hydroxylamine, which are condensed with benzoyl chloride in the presence of sodium bicarbonate at 0 to 5 degree temperature to give para-nitrocalixyxerine hydroxamic acid, which is named as NPCHA or PNCHA. This para-nitrocalixyxerine, a rapid and practical procedure for para-nitrocalixyxerine hydroxamic acid has been developed. Here I have shown the comparison of conventional method and microwave method. In microwave method, it is carried out only in 7 minutes, while in conventional method, this process is carried out in 24 hours. And yield is obtained 99% in microwave method, while in conventional method, only 62% yield is obtained. Here para-nitrocalixyxerine is characterized by UV, IR, NMR and mass spectra. This para-nitrocalixyxerine is utilized for the separation and recovery of metal ion using solvent extraction process. Now, what is solvent extraction process? Suppose if we want to separate any metal ion from organic compound or aqueous solution, then for that separatory funnel is required. So what we are doing, we take 25 ml or 5 ppm to 25 ppm of any metal solution. It is mixed with acidic solution to maintain pH or molarity, and it is extracted with dichloromethane solution of any ligand. So it can be organic layer is separated and absorbance is measured, and in this way we can separate any metal ion in ppb or ppm level. So this can be shown with the help of this video. By watching this video, you can understand what is exactly the solvent extraction process.
The technique of liquid-liquid extraction is a form of solvent extraction which is often referred to simply as a separation, and we do this using a separating funnel as shown on the screen. The technique can be used in a range of contexts, and it's important that you understand why you're carrying out a separation in the experiment that you're doing. In this demonstration, to remove impurities which are water soluble. The first step is to remove the magnetic stirring flea from the reaction flask, and we need to wash this with ether to ensure that we don't lose any of our product. We now need to pour the solution of our product into the separating funnel, taking care to avoid any spillages, so it's wise to use a small glass funnel as we pour. Then we can rinse our reaction flask with more ether to ensure that no product is lost. Now we add the water which we're using to wash our reaction mixture with. It's important that you pay attention to your script, which may specify a different solvent and a particular volume that you need to work with. Next, you need to place a stopper in the neck of the separating funnel, and you must ensure that you don't allow this to fall out at any point while you're handling the apparatus. Secure the stopper with one hand and carefully invert the separating funnel. Now you can gently shake the funnel while periodically opening the tap to release pressure. Normally you carry out these steps several times to ensure thorough mixing of the two layers. And then with the tap closed, you can carefully replace the funnel in the ring on the clamp stand. Here you can clearly see the two separate layers in the funnel. In this case, the denser aqueous layer is at the bottom and the ether layer is on top. However, you should never make assumptions about which layer is which, and you may be given instructions that tell you how to test which layer is organic and which is aqueous. Before running any solvent out of the funnel, you must first remove the stopper. Not doing so is a common error which will prevent the solvent from running freely. Now you should place an appropriately sized conical flask under the separating funnel before carefully opening the tap to allow the lower layer to run out. You should watch patiently as the interface between the two layers moves towards the tap so you are able to stop the flow once all of the lower layer has been removed. Remember that in this case, the lower layer was the aqueous layer. Now you can remove this flask and place a second clean conical flask under the separating funnel to collect the upper layer. As always, you should check your script to see what you've got to do next. You may be expected to return one of the layers to the separating funnel to carry out further extraction steps. In this case, however, we are simply going to dry the organic layer using magnesium sulfate. Other drying agents that may be used could include calcium chloride and sodium sulfate, so make sure you read the script before proceeding. If the drying agent forms clumps as shown here, that's a sign that the solution is still wet and that more drying agent is required. When you can see a snowstorm effect like this, you know that the solution is dry and that no more drying agent is needed. You can now remove the drying agent by gravity filtration before consulting the script once again to identify your next step.
This para-nitrocalix-6-serine hydroxomic acid is utilized for the separation and recovery of vanadium ion in food, biological and environmental sample using solvent extraction process. But in order to know what time of extraction is suitable for the precise determination of vanadium, kinetic extraction study was undertaken. Kinetic extraction not only provides the information for optimizing the process, but it also clarifying the mechanism of the reaction. For that, various factors to optimize extraction, that is rate, hydrogen ion concentration and reagent concentration were studied and rate constant were calculated. The extraction of vanadium with para-nitrocalciferine hydroxomic acid, which is named as NPCHA, has been studied at 6.5 molar of HCl, and concentration of vanadium is measured at different time intervals. If we plot a graph of log V0 versus Vt versus time using k is equal to 2.303 upon T log C0 upon C, which gives straight line with slope unity. This indicates that reaction is of pseudo first order with respect to vanadium ion, and the value of rate constant 0.8106 mole liter inverse second inverse was calculated from the slope. Reaction order with respect to HCl concentration. The extraction of vanadium with NPCHA is carried out at different molarity of HCl solution, and K0 rate constant is calculated. If we draw a graph of log K0 versus different molarity of HCl solution, then it gives straight line. This indicates that reaction is of pseudo first order with respect to hydrogen ion concentration. Effect of pH on the extraction of vanadium ion. The extraction of vanadium with NPCHA is carried out at different molarity of HCl solution. The maximum absorbance of the complex is obtained at pH 6.5. As the concentration of acid decreases or increases, percentage of extraction decreases. So all the extraction is carried out at 6.5 molar of HCl. Reaction order with respect to concentration of NPCHA in organic phase. The extraction of the influence of NPCHA was studied by taking fixed amount of vanadium with varying concentration of reagent concentration. And if we draw a graph of log K0 versus different reagent concentration, then that also gives straight line, which indicate that reaction is of pseudo first order with respect to reagent concentration. The influence of NPCHA was studied by taking fixed amount of vanadium with varying concentration of NPCHA like 2 ml, 4 ml, 6 ml, 8 ml, 10 ml, 12 ml and 15 ml. So 10 ml 6.48 into 10 raised to minus 4 molar of NPCHA is adequate for the quantitative extraction of vanadium. Excess of reagent has no side effect, but at lower concentration, percentage of extraction decreases. Stoichiometry of the complex indicate that 1 mole of vanadium requires 1 mole of NPCHA. Result and discussion. Vanadium and reagent that is NPCHA complex is violet in color and has maximum absorbance at 517 nm with molar absorbability 4.54 into 10 raised to 4 liter mole inverse centimeter inverse. Reagent black does not absorb at this wavelength, and this complex obeys Beer's law in the range of 0.2 to 1.01 ppm of vanadium at 517 nanometer. Effect of diverse ion. The vanadium was extracted in the presence of large number of competitive ion at 6.55 molar of HCl, but none of them affected the absorbance of vanadium NPCHA complexes. Determination of vanadium 4 and vanadium 5 in a mixture. Suppose in a mixture vanadium 4 and vanadium 5 is given, then vanadium 5 is extracted with NPCHA at 6.5 molar of HCl. Organic layer is separated and concentration of vanadium 5 is measured spectrophotometrically, while vanadium 4 remain in aqueous layer. So 0.1 molar KMnO4 is added. So vanadium 4 is oxidized to vanadium 5 and then it is extracted with NPCHA. So organic layer is separated and concentration of vanadium 5 is measured spectrophotometrically. In this way we can separate vanadium 4 and vanadium 5 from the mixture. In order to check the applicability of this method, vanadium is determined in standard steel sample. The result obtained are in good agreement with the certified value. This para-nitrocalciferine hydroxomic acid is used for the separation and recovery of lanthanum by ICP-MS. For that, various factors to optimize extraction, that is rate, lanthanum and cerium ion concentration were studied and rate constant were calculated. The kinetic extraction studies of lanthanum and cerium with NPCHA were carried out with respect to hydrogen ion and reagent concentration. It indicates that reaction is of pseudo first order with respect to lanthanum and cerium, and the value of rate constant 0.485 and 0.400 mole liter inverse, second inverse were calculated from the slope, and half-life period were found 1.42 second and 1.73 second for lanthanum and cerium respectively. Effect of pH and time on the extraction of lanthanum and cerium. The extraction of lanthanum and cerium were studied at different pH using buffer solution. The maximum absorbance of the complex were obtained at pH 8.5 for lanthanum and pH 9.5 for cerium. At lower or higher pH, percentage of extraction decreases. So, all the extraction were carried out at pH 8.5 for lanthanum and pH 9.5 for cerium. The influence of NPCHA were studied by taking fixed amount of lanthanum and cerium with varying concentration of reagent concentration from 1 ml to 15 ml. 10 ml 6.48 into 10 raised to minus 4 molar of NPCHA is adequate for the quantitative extraction of lanthanum and cerium. Excess of reagent has no side effect, but at lower concentration, percentage of extraction decreases. Stoichiometry of the complex indicate that 1 mole of lanthanum and cerium requires 1 mole of reagent, that is NPCHA. Result and discussion. Lanthanum and NPCHA complex has maximum absorbance at 377 nm with molar absorbability 4.51 into 10 raised to 4 liter mole inverse centimeter inverse, and it obeys Bayer's law in the range of 0.5 to 277 ppm, while pinkish red colored complex cerium NPCHA complex has maximum absorbance at 452 nm with molar absorbability 4.50